Proof by induction part 2. Proof by induction that the sum of r from r equals 1 to n is equal to n into bracket n plus 1 over 2 close bracket. This is showing the addition of natural number. So if I have natural numbers such as 1 plus 2 plus 3 plus 4 and so on, and then get to n, that's what this is saying. So if n, let's say n equals 4, and I'm adding 1 plus 2 plus 3 plus 4 all together, and that means 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 3 is 10. So what that meant is if n is 4, because that's up to 4 now, 1 to 4. So if n is 4, and I do 4 plus 1 over 2, I should get 10, which means 4 times 5 over 2, and that's 20 over 2, which is 10. So this is adding all the natural numbers. So n, the last number. And in this case, I need to do, first of all, I need to show that the statement is true for n equals 1. And to show that the statement is true for n equals 1, I need to look at the left-hand side, so the sum, which means I need to say that for n, sum of 1, r equals 1, because my n is equal to 1, and then the r is 1 as well, because r is 1, so the answer will be 1. I'm just adding to the 1, so that's the left hand side. And if I look at the right hand side, and for the right hand side here, I have 1 for n, because I'm making n equals 1 into bracket 1 plus 1 over 2, and that would be 1 times 2 over 2 equals 2 over 2, and that equals 1. So basically the left is equal to the right hand side, and so for n equals to 1 is true, because I get 1 on the left hand side here. When I put 1 there, I just get 1, and on the right hand side is 1. This sign here is sigma. It means summation, so you're adding the natural numbers 1 plus 2 plus 3 plus 4, and that's what this summation is for. So if I add the first 10 numbers of natural number, I have to do 10 into bracket 10 plus 1 over 2, and that will be 10 times 11 over 2, and that is 110 over 2, and the answer will be 55. So that's what this formula is for. But I've proved now that when n equals to 1, I've shown that on the left hand side is 1 and on the right hand side is 1. All I need to do is just this proof here, that and that, and so that is equal to that, so that's good. So the next stage, I need to make n equals k. I need to substitute n equals k. So in this case, I would do basically that. So the summation is n, r equals 1, r. And so what I need to do is basically replace n as k, and don't forget this is n into bracket n plus 1 over 2. What I need to do is say that the summation k r equals 1, that will be equal to k into bracket k plus 1 over 2. So that's what that summation will be. So I'm transforming that into that by saying n equals k. So this is what I need to do here, and that's it. But I'm going to use this here in the next stage, part 3. So for part 3, I need to prove this statement is true for n equals k, which meant that for the statement, so the statement is that the sum n r equals 1, r, and that equals n into bracket n plus 1 over 2. Now n equals k plus 1, so that would be equal to, I would say, k plus 1 sum r equals 1, r, and that I need to find. I need to be able to show that it's going to be k plus 1, k plus 2 over 2. Why? Because once I've replaced that with k plus 1, so that will be k plus 1 plus 1, so that will be k plus 2, and this is k plus 1 because this is k plus 1 over 2. So I need to be able to prove that by what I'm going to do next. So the transformation for that will be, I'm going to use so if I write the sum k plus 1 r equals 1 r, and then I would write sum equals k r equals 1 r, that will be plus k plus 1, the last number. So we add up to k, and then we're going to add the last number, k plus 1. So k plus 1 is the last number. But we already know what this one is. We got it from here. So we're going to substitute that, and by saying that that will be, well, k into bracket k plus 1 over 2. So that's what this is. It's this one here, because it's here already. See that? It's that. And so we're using it here. And then we're going to add that to the last number, k plus 1. We need to take the common factor out from these two. K plus 1 is a common factor. So we can then say, let's do it here so we have room. So we say k plus 1 is a common factor, which means if I take k plus 1 out, I'm going to get k over 2 plus 1, because this is k plus 1 times 1. So if I put that in a bracket to make it obvious, what I meant is that was in a bracket. So that will be k plus 1 times 1. So this is times 1 here. So that's that one, because I've taken k plus 1 out. And I need to take a half out as well. So if I take a half out, which means I'm going to now have k plus 1 over 2. Let's do square bracket. So that'll just be k left, because if I multiply a half by k, I get k over 2 plus 2. So if I multiply a half by, so this means divided by k divided by 2. 2 divided by 2 would be 1. So if I multiply the half back in, I get 1. But this 2 is what I got here. So that's what I need to prove, and I've just proved that. But to prove this, I need to use this assumption 2 in 3 in order to prove that last proof for 3. So I needed to use assumption 2 here, which is what I've done. So I've used it here to now prove that 3 is true. So therefore, I could split it up if I want to. K plus 1 over 2, open bracket, k plus 1, then plus 1. Let's put square bracket there to just keep it simple. So you can see it, that has now proved that. That's for the first one here, we've proved that this is k plus 1, which is that, over 2 obviously, and k plus 1, that's k plus 1 plus 1, which is what that is, So how do we do that? We use the assumption number 2 in 3 to be able to derive that. So we've proved that now, which is what we needed, and that as well. So finally, we need to now do a number 4, where we need to write the for statement. The first one being that since the statement is true for n equals 1, and if the statement is true for n equals k, which what we've done, then it is true for n equals k plus 1, which we did. And finally, the statement must be true for all value of n greater than 1 or equal to 1.